One of the most common applications of vectors is within physics and mechanics. Remember that vectors have direction and magnitude, which means we know which way they're going as well as how big they are. Velocity is the classic example. Velocity is kind of like speed, but speed doesn't specify which way you're going, whereas velocity does. So 7 miles an hour might be a speed, but 7 miles an hour due north will be a velocity. Often the vectors are represented with either a diagram, which will be an arrow, where usually the length represents the magnitude or the size of the vector, and the direction the arrow is pointing represents the direction of the vector. But you can also represent them with a column. 2 or 3D vectors, you would have a vertical column, and you could also use the ij form or ijk form, where you represent each of the 3 components as multiples of the unit vectors I, j and k, which point in the directions of the positive x, y and z axes respectively. See if you can come up with a list of things in mechanics which are vectors. We've got you started with velocity, see how many more you can list. Pause the video, see how many you can write down, and if you've got any you can think of that you write down and think, oh no, that's not a vector, it's a scalar, keep a separate list of those, see how many you can come up with. Alright, so let's go. Vector quantities include displacement, which is usually measured in meters. We might represent it with the letter x or s. In the suvat equations we use s. A lot of the rest of the time we use x. If you calculate the size of the displacement, that would just be a distance. So your displacement from your starting point might be 10 meters, but the overall distance you travel, depending on whether or not you changed direction, might be different to 10 meters. But roughly speaking, if you calculate the size of your displacement, the magnitude of your displacement would represent a distance, maybe the distance you are from your starting point, not necessarily the same as the total distance you've traveled throughout the entire motion. The other one we've mentioned, velocity, measured in meters per second and usually represented by v, although if it's in suvat equations and it's the initial velocity, you would have a u. And if you calculate the size of the velocity, it tells you the speed that you're going. Acceleration, the rate of change of velocity. Now this one's a bit of a weird one in terms of the wording, because we use the same word, acceleration, to represent the vector and the scalar version. So to distinguish between them, if a question asks you for the acceleration and they mean the vector, they will either say acceleration or they'll say the acceleration vector. If they only want the size, they will almost always ask for the magnitude of the acceleration. In the one-dimensional situation, that means if they say find the acceleration and you get an answer of 3 meters per second, you need to consider which way you were treating as the forwards direction, because you need to include that in your answer. Otherwise, all you're giving is the size of the acceleration instead of the actual acceleration, which includes the direction. Another one which goes along with this is force. Because force equals mass times acceleration, it makes sense that force would also be a vector. Force has a size, of course, but it also has a direction. So the direction in which you point a force, or the direction in which a force acts, obviously has a big impact. So it matters which way the forces point. You might have written down some specific forces as well. The weight force, which you usually represent with mg, m the mass multiplied by g the acceleration due to gravity. That is a vector because although the mass is not a vector, it's just a scalar, it's just a number with a size but no direction. When you multiply that scalar by the vector g, which represents the acceleration vector of gravity, the acceleration due to gravity, 9.81 meters per second downwards, then you get a velocity, then you get a vector. Friction is a vector. The direction of the friction will be the opposite direction to either the motion that's taking place or the motion that would take place if friction wasn't there. Normal reaction, the direction of this one is kind of given within the name as well. The direction is normal to the surface, or normal as in perpendicular to the direction of potential motion, and we usually represent that one with a capital R. Here's a few scalars that you might have had. Time is a very common thing that we use in mechanics, but it does not have a direction in the same sense that the others do. So you might end up with negative values for time, but we treat it as a scalar. So the negative we just think of as being, well, that happened before the beginning of motion, but it's more of an arbitrary starting point rather than a measure of the direction. Time only goes one way, so time is a scalar quantity. Think of it like temperature. Temperature doesn't have a direction, even though you can have positive and negative temperatures. Mass is definitely a scalar. You can't have a negative mass, so it's even more obvious than with time or temperature. And it doesn't have a direction. The thing that gives mass an apparent direction is when you multiply it by the acceleration due to gravity, then you get weight, and weight does have direction. So if you're thinking of mass as having a direction, what you're probably confusing it with is weight. Weight pulls you down. Mass doesn't have a natural direction. If you go off into interstellar space, you'll find that your mass just gives you inertia. It makes you harder to accelerate forwards or to decelerate backwards. It doesn't automatically direct you in any particular way. The coefficient of friction. The frictional force we've mentioned earlier is a vector, but the coefficient of friction, mu, doesn't even have any units. And it is not a vector, it's a scalar. In fact, it's just a ratio between two forces. So we've got the, and not only that, but between the size of the two forces, because the directions of the normal reaction and the frictional force are not even the same. The normal reaction points perpendicular to the potential motion. The friction points in the opposite direction to potential motion, so parallel to it, but in the opposite sense. Mu is just the number that tells you the scaling factor between the two. So if you've got a normal reaction of 100 newtons and mu is 0.2, then it tells you the size of the frictional force, or the maximum size of the frictional force, is 0.2 times 100, or 20 newtons. So it's not a vector, it doesn't have a direction, it's just a scaling factor between two forces. Energy. We don't go into energy in the current A-level maths, but you may well have come across it in physics. Energy is measured in joules. It's to do with the potential to do work in the physics sense. In other words, to get stuff done, to move something by exerting a force over a given distance. And although a force has a direction and distance has a direction, the energy, because it's a combination of those two, it's more about the potential to do that, and energy itself does not have a direction. Power is the rate at which energy is transferred. So if you move a car from one end of a street to another, but it takes you 30 minutes because you're pushing it by hand, then that's a fairly low power rating. But if you move it from one end of the street to another and you do it in a third of a second, that's because you're using a very powerful engine. You can boil a lot more water if you have a kettle with a higher power rating. But again, that's just the capacity for something to transfer energy, and it doesn't have a direction. So let's look at how we use vectors in a mechanics context. Most of the equations that you'll recognize that you've been using in mechanics so far, if they involve vector quantities, usually you can use them with vectors, but not always. So have a look down these, see if you can identify within each one which of the variables are vectors and which are scalars. You might want to copy out the list and then do the standard method of underlining the letters that represent vector quantities and not underlining the ones that represent scalars. In textbooks, etc., you'll see vectors often represented in bold and scalars just in ordinary print, but you can underline things. I'll pause for a second, or you should pause for a second, see if you can make a note of which of these have vectors and which of them you think would work with vectors. There's at least one that won't work, so see if you can spot them. Alright, here's the first one. This works just fine. We can have displacement equal to the initial velocity multiplied by time. Although we can't multiply vectors together, we can do a vector multiplied by a scalar. If we got the vector 3, 4, we can times it by 10 and get the vector 30, 40. So that's not a problem. We've got t squared. T is just a scalar, so we can square it. That's no problem. We can multiply it by a half. We can then multiply it by the vector a for acceleration. The next one is just as good. We can start with the initial velocity vector. We can add on t multiplied by the acceleration vector, and it will give us the final velocity vector. Another one that works is s equals u plus v over 2 times t. Although it may seem a bit weird to average two vectors, it still kind of works. We can think of it as add the two vectors, u plus v, term by term, add the I components, add the j components, add the k components if it has them, and then multiply the entire thing by the scalar quantity a half, and that will give you a vector which is halfway between u and v, in the sense that if u is pointing the same way as v, then the vector u plus v over 2 will be pointing the same way as both of them, but its size will be halfway between the two. If they're pointing in different directions, it gets a little more complicated, but it's still like an average. And in fact, you can think of it like the midpoint between 2 points in space. If you've got the coordinates of a couple of points and you take the average of the x coordinates, the average of the y coordinates, you'll get a midpoint. And the vector that takes you to that midpoint would be like the average of the two vectors that take you to the two endpoints. When you've got that vector, the average velocity vector, you can multiply it by t, which is a scalar, and it gives you the displacement. The only other one on this list that works is F equals ma. F, the force, is a vector and it has direction. A is an acceleration, it is a vector and it has a direction. The mass is not a vector, it's just a scalar quantity, but when you multiply that mass by the acceleration vector, it gives you the force vector. Now, this one doesn't work, v squared equals u squared plus 2as, because it would require you to multiply vectors together. We can't square a vector. We can't do the velocity vector v multiplied by itself, not in the sense that this formula is referring to. In fact, one of the reasons this formula doesn't work is that it's very closely related to the conservation of energy formula for kinetic energy. If kinetic energy is half mv squared, then the initial kinetic energy is half mu squared, and the work done will be force times distance, or F times s, or ma times s. And if you have half mv squared equals half mu squared plus mas, and you multiply everything by 2 and divide everything by m, you get this formula. So this formula is essentially saying whatever movement energy you have at the end, that's equal to the movement energy you have at the beginning plus any additional energy put into the system along the way. And because that's an energy equation, it doesn't work with vectors. You would have to calculate the size of those in order to work out something about them, but that would then lose you information about the vectors themselves. The other one that doesn't work with vectors is F equals mu r. We mentioned briefly F and R are both forces and they both have direction if you think of them as their original forces, but in this formula you can't multiply the vector r by a scalar quantity and end up with the vector f, because r and f are not parallel. If you remember, parallel vectors are scalar multiples of each other. So in order to use that formula, which is the formula for the maximum frictional force, you would need to refer to the size of the forces. Here's what those four equations that work look like if we make the vectors bold. You'll notice mass and time are the scalar quantities, and everywhere where a vector appears, it is either multiplied by a scalar, or it's just added to other vectors, or it's divided by a number which is equivalent to multiplying by a scalar. Right, let's try an example. Let's have a quick look back and remind ourselves the suvat equations we've talked about. We've already used them in the context of what I would think of as one-dimensional vectors. In other words, directed numbers. It's a fancy word for numbers that include negatives. So if you're allowed negative numbers, you are effectively introducing a complete directional system. You can go forwards and backwards. You can go up and down. So if you have 3 meters per second for one of your velocity values, you have negative 3 meters per second for the other one, it means that one of them is going in the opposite direction to the other. We use negative 9.81 when we're referring to the acceleration due to gravity, so that we can take into account not just the size of that acceleration, but also the direction. And you already know from making many sign errors with suvat equations that the signs matter. getting those negative signs in the right place makes a difference when it comes to correctly solving suvat equations, even when you're dealing with the one-dimensional case. You've already done two-dimensional suvat in the year 1 content. That would be questions like this. You've got u, you've got v, you've got t, you're asked for the acceleration. And the best way is to write out the formula, substitute in the vectors, and then rearrange carefully. Don't go dividing a vector by a vector. You want to think about how you can rearrange this in such a way that at each point you're doing something sensible that can be done with vectors. I'm subtracting the vector 3, 4 from each side. I can simplify that, 6 minus 3 on the top and minus 2 take away 4 on the bottom. And then we can divide everything by 6, or if you prefer, multiply everything by 1/6. And that's just a scalar that we can multiply the vector by. So a 6th of 3 and a 6th of -6. And that gives you the acceleration vector. You can see that the direction of the acceleration vector is identical to the direction of 3, -6. We've just shrunk it by dividing by 6. 3D, it works just the same. There are some nuances you want to be aware of. So for instance, in this one, because it's t that we don't know, you've been given the vectors for s, u and a, but you don't know t. So the idea would be you find the appropriate formula. You've got 3 things, you want a 4th thing, so there's definitely going to be an appropriate suvat equation for you. And when you've identified it, remember they're in the formula book, you write it out, you substitute the numbers in. But then for this one, we're going to take advantage of the fact that if 2 vectors are equal, then every single component of the first one matches or is equal to the corresponding component of the other one. So on the right hand side we simplify that completely, and we end up with 0 times t add 1 times t squared, and that is where the t squared comes from here. That bit is this, 0 times t plus 1 times t squared. If you're a little uncomfortable doing it all in one line, then you can write out 0, 1, 1 multiplied by t, it'll give you 0 tt, and then 1, 2.5, -1/2 multiplied by t squared, 2.5 t squared, -1/2 t squared. But you'll see those bits appearing. So the second component, the j component, is t, 1 times t, add 2.5 t squared, t plus 2.5 t squared. And the k component, t -1/2 t squared, comes from 1 times t -1/2 times t squared. And in each case, they've been equated to the appropriate component on the left-hand side. And you can see that because each one is a quadratic, there are actually 2 potential solutions to each. All we need to do now is recognize that because t must be either 4 or -4, and t must be either 4 or -4.4, and t must be either 4 or -2, since there must be a value of t that satisfies all of those, the vectors can't be equal unless they're all true, we have to look for any values of t that fit all 3 conditions. And the only value of t that satisfies that is t equals 4. So that's how you solve that sort. This next one involves forces. And the key idea with forces when it comes to vectors is that vectors are an incredibly intuitive and easy way to combine forces. There are a whole bunch of forces involved in this question. We are talking about an aeroplane of mass 1200 kilograms flying. So we have I and J representing east and north directions, and K represents vertically upwards. We have the forces of thrust, which is the force that pushes the airplane forwards. Lift pushes it upwards, mostly provided by the wings. And the combined forces of wind and air resistance, called capital F. Each of those has been given to us in IJK form. And if we want to find the overall resultant, the net effect of all of those, we just add them all together. The counteracting, the cancelling out that might occur, and the combining that you'll end up with, that all automatically happens if the vectors are already written separated out in this form. So we've got the I components, J components, K components, or the first, second and third rows of that column vector. When we put them together, If there's two that are working together, we'll see the combined effect. We'll get one single larger term, and if there are two that are somehow in contrast to each other, one's forwards, one backward, then those terms will cancel out. There's one other thing to be aware of in this particular question. It's asked us for the magnitude of the acceleration. You'll notice it says magnitude of the acceleration, so we're going to look for the size of the acceleration vector. But before we get that, we're going to need to find the acceleration vector itself. It's important to notice that if you just work out the size of all the forces and add them together, that won't be accurate. Here's a really simple example to show why. If I push on something with a force of 3 newtons and it pushes back at me with a force of 3 newtons, then there isn't a net force of 6 newtons. The thing is not accelerating. The net force is 0 because the 3 newtons pushing back on me was in a different direction. Now the forces we're looking at here are in all sorts of different directions, but when we combine them, that's the only way we figure out what the direction of the resultant force is and how big that resultant force is. Once we know that, we can find the acceleration vector, and once we know that, we can find the magnitude of the acceleration. Now we've got a mass of 1200 and we're given T, L and F. There's one more thing we need to calculate. Thrust is the force that the aeroplane's engines are providing. Lift is the force pushing it up, the wind from underneath, the effect of the wings. And F is the air resistance and the wind. There's something else which the plane will have, and that's its own weight. So we're going to take that into account first. The weight of the plane will be calculated using the mass, which we were told, and G. Now, I'll be honest, when I first read this, I nearly forgot the weight, and then I looked at the question and I thought, why have they told me G? What's the relevance of that? And then I realized, well, they probably give me G because it matters. It's important for the question. Chances are the plane has a weight. Of course it has a weight. The weight will be pulling down. We need to take that into account. The weight we can calculate because we know the mass. And all you need to find the vector for the weight is the mass times the acceleration due to gravity. Now, not everybody uses the column form for these questions. A lot of people like to use I, J and K. I think in the textbook it's mostly I, J and K because it's easier to fit onto single lines. It takes up a lot of space when you do it in column form, but I prefer it in column form because we can see if there are 3 equations, for instance, combined within our vector equation, we can see each of them. They're all on separate lines, and it's clearer to me to see what's there and what's not. L, for instance, lift, only has a K component. That means its I component and J component are both 0. That's representative of a force which doesn't push to the east and it doesn't push to the north or west or south because they're just the negatives of the I and J components. All it does is push upwards. And a similar thing, the F, which represents the wind and air resistance, that moves the plane in the negative east direction, so west, and in the positive north direction, but not at all vertically, so it doesn't push it up or down. The thrust, interestingly, apart from the east and the north, which are determining which direction the plane is trying to fly in, thrust also provides some upwards effect. So if the nose of the plane is pointing slightly upwards and you fire the engines, then it's going to push the plane in the upwards direction a little bit as well as in the forwards direction, whichever way it's pointing. Now we can put them all together and we include the weight into that, and the reason we put them together is that if we want the acceleration, we have to have the resultant force. We care about the overall net force acting on this object. So we add all 4 of those forces together and we say that's equal to mass 1200 multiplied by A, the acceleration vector. And all the way through here it remains a vector right until this point here. So we add all those vectors together term by term, 0, add 2800, add 0, add negative 900, that gave us the 1900, and so on for the other terms. Then to get the acceleration itself we divide by 1200 and we get this relatively messy thing. But that is the acceleration vector. Positive in the north direction, in the east direction, negative in the north direction, and negative in the up direction. We can find the magnitude of the acceleration like it's asked us for just by using old school Pythagoras. So square each of the components, add them together, square root. Remember, in 3D it's just the same as in 2D. Square every component, add them all together and square root. I'd recommend writing the exact version but also rounding, because this is a mechanics question. It is by its nature an approximation for something in real life, so the true answer is unlikely to be some perfect irrational number like root 1531 over 20. So we give an answer rounded to a reasonable level of precision. For the next part of the question, part B, determine whether the aeroplane is ascending or descending. We'll start with that bit. Ascending means going up. So it's just a case of looking at our acceleration vector, or in fact looking at the resultant force vector. Either of those makes no difference. All we care about is the overall force in the upwards direction or in the downwards direction. Now there are two aspects to this. One of them is it is accelerating downwards. There's a negative there, so you might think immediately, oh, obviously downwards, because it's got a negative upwards force. But it doesn't say whether the force is upwards or downwards. It says, is the aeroplane ascending or descending? So we need to look for a slightly more subtle clue. The aeroplane is initially in level flight. If it had been shooting upwards at a rapid velocity, the fact that it's accelerating downwards doesn't necessarily mean it's moving downwards. You can simulate the same effect by grabbing your calculator and throwing it into the air. And as you do that, while it's on its way up, it's moving upwards. You would say it's ascending, and yet gravity, the only force that has a significant effect on it, is making it accelerate downwards. So just because you have a negative vertical acceleration does not necessarily mean you are moving downwards. It just means eventually you will, if the situation continues. But in this case, it is descending, partly since the k component is less than 0, but also relying on the fact that we are initially in level flight. So you've got to make a note of that and recognize that that is an important part of this answer. The next bit says find the size of the obtuse angle its acceleration makes with the vector k. Well, luckily for us, we've recently learned how to find the angle between a vector and any of the coordinate axes. And since k just represents the third coordinate axis, the z-axis, we can use the same kind of formula. All we need is the k component on the top, and that's this thing, divided by the magnitude of the vector, which we already calculated from here. That gives us cos of the angle we care about. And when you do inverse cos, you can find the angle, and we can check as well, because it said we were looking for an obtuse angle, so we can verify for ourselves that this answer works. If you've got a book which is the same edition as mine, the answer in the back might tell you it's 101.9 degrees. So if you double check Solution Bank, it'll give you the more accurate result. It should be 101.3. Here's one more example. Tom is on a fairground ride, and we now have a vector representing his position, but each of the components is a function of t, the time that goes by. Perpendicular unit vectors I and j are in the horizontal plane. That means those two are lying flat, if you like. So if you're holding a map, you'll be able to see the I and the j directions just like you would see the x and the y axes on a graph. You can think of them as east and north, if you like, as they often are, but the vector k is directed vertically upwards. So just like with the last one, we're thinking of that third component k as being in the upwards direction. Find Tom's position vector when t equals 0. Well, we can start by putting this into a column, and then we just substitute 0 into that. When t is 0, we get 2 cos 0, 2 sine 0, and 10 minus 0.4 times 0. 2, 0, 10. So that's where he starts, basically. He's already at a height of 10. The position vector when t equals 2 pi. Now, you might notice that because cos and sine are periodic, and they have period 2 pi, we're going to get the same results for the I component and the j component as we just did, but not the k component. because although the I and J components will cycle back round every 360 degrees, or rather every 2 pi radians, the K component is just going to continue to go down, 10 minus 0.4 times t. The bigger t gets, the smaller the K component becomes. The last bit, write down the first two values of t for which Tom is directly below his starting point. We already know his starting point, 2, 0, 10. Directly below means the I and J components have to match. So the first time he's directly below is actually this that we've just calculated here. This happens when t equals 2 pi. The I and the J components are identical, which means that he's in the same position on a map, let's say. But if you were to look at where he is in reality, 2, 0, 10 is a little higher than 2, 0, 7.49. Because by the time we get to this second one, after 6.3 seconds or thereabouts, after 2 pi seconds, then the position of Tom relative to his previous position is about 2.5 meters below. And if we wait for another cycle, we'll get right back to the same place. So when will 2 cos t be 2 again? Well, that's going to happen a couple of times within each cycle. But when will 2 sine t be 0 again? Again, a couple of times, but there's only one moment when they're both 0 again. We'd have to wait until t equals 4 pi. Lastly, let's have a quick look at the picture of what's going on. A starts up high, and it's following what would look like a circle from above, but as we look at it in 3D, we can see that it's essentially spiraling down. This is a classic maneuver for fighter pilots back in the day, 100 years ago. You go into a spin if you want to lose altitude quickly, and you can spiral down. You're following a circle, so from above it might look like you're just going in a circle, but from the side you would see the altitude dropping as you go all the way down. That's the kind of motion that this one's describing.